I'm Luke, and I'm the programming lead for Team 6133, The Nut, and I'll be speaking about computer vision and FDC. In order to evaluate different computer vision techniques and technologies, we first need to understand why computer vision is useful in FDC. Each season, there is some sort of randomization that the robots must detect on their own. One of the most powerful and consistent ways to do this is using a camera on the robot. Teams have used computer vision to detect the starter stack in Ultimate Goal, find the Sky Stone in Sky Stone, sampling in Roboruckus, and even for beacons, up until and including the Velocity Vortex. The common theme in all of these is detecting the configuration of game elements that are distinguishable primarily by color. However, computer vision can be used much more powerfully to enhance your autonomous and even teleop, as we'll see later. Computer vision is at its roots, it's just extracting meaning from visual data. In our case, data from the phone camera or a USB webcam. There are simple but effective approaches that maintain semantics very close to direct pixel manipulation, while others may use more complex mechanisms from edge detection to neural networks in order to operate. First, we'll go over some of the basic techniques for computer vision in FDC. One of the most common approaches for analyzing game elements after randomization is just sampling the pixel values of a small box in the camera frame. Teams typically take the average color of the area and compare it against known values for the game element's color, determining whether that area is occupied by an element or by which source. This is a simple and easy way to solve many of the game's vision problems and get a decent result. However, this approach has its downsides. One of the biggest is that it can fail when the robot is not perfectly set up. It will look in the wrong place on the field to find the game element and may have unexpected results. It is also almost entirely limited to use in initialization, when you can be fairly certain of the position of the robot in your randomized element. This is because it needs to know exactly where in the frame to look for the object. When looking for objects in the frame and comparing pixel values, there are many different ways to encode the same colors, called color spaces. OpenCV, as well as most commercial image formats, default to RGB representation of colors, which add up to the red, green, and blue components of a color. While convenient for displaying colors using RGB LEDs, this is usually not the best option for analyzing an image. Other spaces include the HSV or YCBCR, which are very useful for making more sense out of a color. For example, to select only colors that are pure blue, like the wobble goal, but of a wide range of saturations and values, HSV is a great option. To find orange rings on the field, this year we used YCBCR and focused on the chroma channels, with a high chroma red and a low chroma blue. Converting images between color spaces can allow you to tune better thresholds. No matter what color space you are in, it is extremely important to test your code under many different lighting conditions, because you never know what a tournament will be like. Besides simply searching known rectangles on the field of view, there are other ways to find the sampling point. A more advanced variant of this is relying on contour detection to find where to look in the image. Contour detection is a feature offered by many computer vision libraries, such as OpenCV. It allows you to locate the edges in a picture. When used directly on the raw image, it can be pretty messy, but when you apply transformations to the image first to improve its edges and weed out what you don't want, contours become a powerful tool. The image depicts the first and last stages in our pipeline. In between, the pixels of the image are filtered so that all non-blue pixels become black and all blue pixels become white. Once this binary bitmap has been created, we can find the coordinates within our frame of the wobble goal using contour detection. Supplemented with these other techniques, contour detection is very powerful and versatile for finding elements in the field because it does not rely on hard-coded coordinates. However, it is not always the best tool for the job. Implementing a proper pipeline with contours can take time and be hard to maintain and hard to tune. The contour technique saw a rise in popularity last year after our team contributed a sample pipeline to FDC Lib using it, an open source library for FDC. Many users of this library have had great success with the vision, and we hope to see it continue to grow this year. One other option that kind of strays so far from OpenCV and manual detection is neural networks. Neural networks are a way to bring machine learning into your computer vision code. They have been used to great success both academically and industrially, and can outperform custom OpenCV models with enough training data and good procedures. Here are some examples of statistics from neural networks. As you can see, some convolutional neural networks have been able to get error rates on the scale of tenths of a percent. And these are great statistics that show that neural networks are very promising for the future of computer vision. However, those successful models in that statistics took 70,000 images of training data to produce. We could only analyze images that were 28 pixels wide and 28 pixels tall, and were all black and white. Neural networks take a lot of work to prepare the training and testing data for, and might not produce good results depending on how you manipulate that data in a network in the training process. One upside of neural networks is that FIRST has in the past maintained sample TensorFlow models to make vision easier for new teams. However, it has historically not always been superior to custom models or other approaches. The major reason to opt for neural networks instead of OpenCV in certain cases is for difficult differentiation and recognition problems. They're too complicated to solve effectively using OpenCV. However, other methods do always exist for some of these, and you can research and implement them. Whether you choose to proceed with OpenCV, TensorFlow, or another technology, one great tool to enhance your computer vision workflow is Jupyter Notebook in the interpreted languages such as Python or JavaScript. Using these in conjunction allow you to rapidly edit, test, and document code in your browser with rich text editing, charts, graphs, and image previews. All of these prove extremely helpful for writing and debugging computer vision code. This code shows a sample Jupyter block to analyze and display the stages of a vision pipeline for a whirlpool. And the images on the right likewise show 3 original images along with their process counterparts for calculating the height of the starter stack. Once you have completed a working prototype in Jupyter, you will need to port your code onto the robot. For OpenCV, code can be written either in C++ and called using the Java native interface, or it can be written in Java, Kotlin, or other JVM languages using EasyOpenCV, a wrapper library for OpenCV. Once the code is running on the bot, it is usually a good idea to stream the image to the driver controller during initialization, so that you can make sure your vision is functioning before they randomize. However, vision is not only used for randomized elements. One of the cooler things we can do with this kind of computer vision, beyond just detecting the randomization, is looking for scoring elements around the field during a match, either in auto or in tele even. One use for this and ultimate goal was picking up rings from the field that were missed or bounced back from power shots autonomously. This bounce back technique actually added 36 points to the max potential auto score, which was very hard to get done right. Besides shooting rings consistently enough to hit the power shot and bounce onto the field, half the challenge lied in finding the rings accurately to intake them again. This can be done very well using computer vision and a technique known as pose estimation. Pose estimation is generally the process of finding elements on the field and finding the position of your own robot using computer vision. It can involve a lot of trig, but at first it helps to imagine the camera frame as a unitless plane in the camera's field of view. Then all the pixels are on their own ray from the focal point of the camera onto the field, and using similar triangles you can find real-world measurements. Here's what that math can look like, not accounting for any camera distortion such as the fisheye effect, as we are dealing with an ideal pinhole camera here. First, we calculate the focal length of the camera. Then we produce a matrix to move the origin of the pixel frame to the center, because they are initially measured from the top left corner. Next, we create helper functions, alpha and beta, to provide the angle from the center of a pixel in an XZ and YZ plane. After that, we define the angles at each of the boundaries and use them along with the fact that rings are 5 inches in radius to convert the coordinates to polar form centered around the camera. Lastly, we can calculate the equivalent Cartesian vector in reference frame of the robot and of the field. This page demonstrates some of the prototyping it took to get to this algorithm. Even more projects were started, including a second camera or a physical marker to improve the results. With computer vision, there is endless room to experiment. That's all we have to share on computer vision. I'd be happy to take any questions.